Hello and welcome to helpyourmath.com. In this video, we're going to look at simplifying fractions, sometimes also known as reducing fractions to their lowest terms. First of all, what is a fraction? Go ahead, tell me what your answer is. If you said that it's a number, you would be correct. That's all a fraction is. It's a number. It's a number in which the unit isn't necessarily 1, or we can think of it as a ratio in which we are told how many parts per whole we have. So for the second definition here, a number in which the unit isn't necessarily 1. When we think about integers and whole numbers, those are the ones that don't have fractions. So like 2, for example, is an integer and a whole number. This is actually two whole units. So that's what I mean when I say the unit isn't necessarily 1. We can turn any whole number or any integer into a fraction simply by putting it over 1. When we're given a fraction, such as 2 over 3, now we're changing what the units are. We're saying now that to complete one whole, we need 3 units, and we only have 2 of those 3 units, so 2/3 is not quite as big as one whole. Let's talk about what it means to simplify a fraction. And before I get started on a definition, I would like to point out that when I say simplify, that means the same thing as reduce to lowest terms. I don't necessarily like that language, but it is used frequently, so I try to make sure that I do use it, even if I don't particularly like it. The fancy way to describe what it means to simplify is that when you write the fraction as integer over integer, the two integers are relatively prime. Now, this is fancy and this uses fancy language. So first, what's an integer? An integer is a number that doesn't have a fraction or decimal. It can be positive, negative, or 0. So 2, -7, 300, those would all be integers. So we take the fraction when it's written as integer over integer, meaning we don't have like a weird decimal or a fraction in either the numerator or the denominator. And then what does it mean that they're relatively prime? In the last example, on the last slide, I used the example 2/3. We would say that 2/3, that 2 and 3 are relatively prime because their only common factor is 1. So 2/3 is simplified, or in simplest form, because 2 and 3 don't have any common factors besides 1. Any fraction that's like that, so for example, if we had 4 over 51, so even though 4 does have factors besides 1, right, it has a factor of 2 and 1 and 4, it doesn't have any common factors with 51 besides 1. 51 has factors 3, 17, 51, and 1. So 4 over 51 would also be in simplest form or in lowest terms because the 4 and the 51 only have a common factor of 1. So that's what that means. Why simplify? Well, it makes it easier to compare values. I didn't say easy, I said easier. Let's suppose we had to decide which represents the larger value, and we're given these two fractions. So the first fraction we're given is 2,751 3,668ths. And we want to compare that to 5,426 8,139ths. Yikes. Well, that's not necessarily the greatest thing. I don't really want to deal with those numbers. But if we simplify them, this simplifies to 3 over 4, and this simplifies to 2/3. Now it's a little bit easier to compare. 3/4 means that we have something split into 4 equal parts, and we have 3 of those things. And 2/3 means we have something split into 3 equal parts, and 2 of those things are what we have, right? So now we can much more easily compare, and we know that 3/4 is in fact the larger value. So that's why we like simplifying, just so that way we're consistent and we don't have somebody who says, well, I have 3/4, and somebody else says, well, I have 9/12, and somebody else says, well, I have 15/20, because those all represent the same amount, but it's just much more consistent for everyone to have the 3/4, right? Okay, let's talk about how we can simplify a fraction. We can determine common factors between the numerator and denominator. That's what we're looking for. We're trying to find things besides 1 that go into both the numerator and denominator. We can do this very formally, or we can do this informally. If we do this formally, we would write down the values of the numerator and denominator as products of their prime factors. Then we can cancel out the common factors. So for example, if we have 28 over 70, we want to write 28 as a product of its prime factors. That's called the prime factorization. And we could do that by doing a factor tree, and we could say, okay, well, 28, that's 2 and 14. 2 is prime. 14 is 2 and 7. Those are both prime. So 28 is 2 times 2 times 7. Then we do the same thing for 70. So 70 is 10 times 7, 7's prime, and 10 is 5 times 2, both of which are prime. So we would write it as its prime factors, 2 times 5 times 7. And then if there's a common factor between the numerator and denominator, we can cancel those out. So here we have 2 over 2, so we can cancel those out. Here we have 7 over 7, we can cancel those out, leaving behind 1 times 2 times 1 is 2, 1 times 5 times 1 is 5. So we can simplify formally by listing out the prime factors and then simplifying the prime factors as the case may be. Informally, we can check to see if the numerator and denominator have any common factors. So when I refer to a common factor, I mean common, like normal factors such as 2, 3, 5, or 6. This may require more than one simplification. So if you do this, you have to check and double check that things are completely simplified. So how do we know if something's divisible by 2? Well, if it's even, it's divisible by 2. How do we know if something's divisible by 3? That's where you add up the digits and you see if the sum of the digits is divisible by 3. 5, you look to see if the ones place is a 0 or a 5. And 6, you might just recognize that something's divisible by 6 if you know your multiples really well, or if it's divisible by both 2 and 3. But if it's divisible by both 2 and 3, you're better off just simplifying in 2 steps instead of 1. So for example, 30 over 48. Instead of doing prime factorization, let's just think about anything that goes into both 30 and 48. And there are multiple responses here. So in multiple steps, we can say, okay, well, they're both even, so I know 2 goes into both of them. So I'm going to divide them both by 2. Divide by 2, divide by 2. And then we would end up with 15 over 24. And you'll notice here we divide by the same amount because what we're really doing here is we're dividing by 1. And dividing by 1, we're not changing the value of the fraction. We're just changing the amounts in the numerator and the denominator. But we say that 15 24ths is equal to 30 48ths. Now, 15 is no longer even, so this is no longer divisible by 2 over 2. What about 3? Is 15, does 3 go into 15? Yes, it does. Does 3 go into 24? Yes, it does. So we can divide by 3 over 3. And again, what we're doing when we're dividing by 3 over 3 is we're really just dividing by 1. And dividing by 1, not changing the value. It's just taking off the high heels or taking off the jacket, but it's still the same value underneath it all. When we divide by 3 over 3, we end up with 5 over 8. And 5 and 8 have no common factors besides 1. So we would say that this is the simplified version. Now, we did that in 2 steps. We could do that in 1 step. We divided both the numerator and denominator first by 2 and then by 3, which means we could have done this in 1 step by dividing them both by 6. If I divide the numerator by 6, 30 divided by 6 is 5, 48 divided by 6 is 8. So that would be doing it in 1 step. But it doesn't matter. You can do it in 1 step or 2 steps. Just make sure if you're going to not look for the largest common factor, the greatest common factor, that you check your work. Let's look at some examples. So we have 18 over 48. Can you think about what goes into both 18 and 48? What did you come up with? I think the largest is, again, our friend 6. So let's see if we divide both the numerator and denominator by 6, right? We're dividing by the same amount. So what are we actually dividing this fraction by? We're dividing it by 1. 18 divided by 6 is 3. 48 divided by 6 is 8. And 3 and 8 are relatively prime. So this would be the simplified version of this fraction. How about this example, 45 over 85? Well, I noticed that they both have 5s in the ones place, which means they are both divisible by 5. So I'm going to divide by 5 over 5, which is really dividing by 1. 45 divided by 5 is 9. 85 divided by 5 is 17. And then 9 and 17, they don't have any common factors, so it would be completely simplified as 9 over 17. How about these 2 examples? So we have 63 over 35. I noticed that 63 over 35 is an improper fraction, which means any fraction that's equivalent to it will also be an improper fraction. But what goes into both 63 and 35? This one's a little bit tricky. So if you ever get stuck, do the prime factorization of one of them to see if that can kind of help you find a factor that they have in common. So 35, I know that's 5 times 7. And 5 doesn't go into 63. Does 7? Oh, 7 does, right? Because I can write it as 9 times 7. And then the 7's cancel. There we go. So we can simplify it down to 9/5. And our last example, we have 39 over 91. Yikes. 91 is kind of an interesting, weird number. Eek. It's not divisible by 2 or 3 or 5. So again, what I might do is I might just look at the prime factorization of 39 to see if I can try to figure out a factor of 91. 39 is 3 times 13. And I know 3 doesn't go into 91, but does 13? 13 times, what do we think? How about times 7? That would be 21. That's looking good. So this is 7 times 13. The 13s will cancel, and we end up with 3 over 7. So when it comes to simplifying fractions, there's a variety of methods that we can use. You can use the formal method, which is the prime factorization. You can look for the common factors like 2, 3, 5, and 6 and see if that works. If you get stuck, just do the prime factorization for 1 just to see if you can find something in common. And sometimes you might, if we have something like 56 over 57, for example, there are a lot of factors. So if we look at 56, that's 7 times 8, okay? And then we could break that down. That's 7 times 4 times 2, so that'd be 7 times 2 times 2 times 2. And 57 is 3 times, what is that? 3 times 19. And so we see here that when we look at the prime factorizations, they have nothing in common. That means that this was already as simplified as it could be. It's already in simplest form, and that's all we can do. So it could come to that too, but at least we checked and we know for sure that that's the case. These have been examples of simplifying fractions. Thank you for stopping by.